Well, I've cleaned up the Hewlett-Packard Model 410B vacuum tube voltmeter. Not to the hilt, but I've cleaned it up so that it's a little bit less distracting to work on, and so that it's a little bit safer to work on. But anyway, it's cleaned up quite nicely. Inside was pretty dirty and pretty dingy, and more needs to be done. What I have not done is I haven't cleaned any of the potentiometers, nor have I made any attempt to clean any of the switches. But what I have done, in addition to cleaning the inside and the outside, is that I have replaced most of the probes, and I've cleaned the power cable. So the power cable actually has cleaned up very nicely. It's increasingly supple and not sticky anymore. And I don't actually see any reason to change the power line. The probe cables, on the other hand, were just a complete disaster, as we saw in the last video. And what I was able to do is I have tacked on, or maybe the verb to hack is a little bit more accurate in this case. I have emplaced temporarily a ground cable, a DC coaxial cable, and the resistance function cable, the Ohms cable. And in the case of the DC cable, I have not fabricated a probe. I have rather, just zoom in a little bit here, what I've done is I've simply tacked on a 22 mega ohm resistor onto the end of the center cable of a coax cable, using mechanically an alligator clip. And you'll see what I want to do here in a few minutes. So the fourth cable that I have not mentioned is the RF probe, or the AC probe. Remember, in the last video we had mentioned that this is a triaxial cable and is more difficult to find, and it's more difficult to work with. But we also noted that it wasn't cracking and that it was somewhat supple. And as I cleaned it off, it has relaxed a bit and become more supple, and the RF probe has cleaned up rather nicely as well. So what I want to do in this video is a couple of things. First of all, what I want to do is I want to just kind of briefly go through the circuit at a very high level and point out some things about this meter. And then, having put temporary probes on this and done a couple of other things internally, like I replaced the single electrolytic capacitor in the unit. It was a filter capacitor, and I tightened up the ballast tube. Had actually come loose, and I had to resolder the connections onto the tube socket. But having done those two things and inspected it visually, I actually want to turn it on now and begin the long troubleshooting process, or maybe I shouldn't assume that there will be troubleshooting. Begin the long process of seeing where this is, what approximately works, what doesn't work, and then beginning to bring this into shape. Let's look at the schematic for this. And the schematic is readily available online for multiple serial numbers through the production period of this meter. I was lucky enough to find, just on the first trial, a schematic that corresponded to the serial number range on this meter. So the first thing, and it's a really important thing to point out, if you just look at the line power supplying this meter. And this was pointed out in one of the comments on the first 410B video, is that this comes with a 3-prong power cord. And so the chassis of this meter is actually grounded, all right? Which means that it's in common with the neutral wire tied in at the entrance box to houses in the United States. So that means that the chassis of this voltmeter, if you were to read the potential difference between the chassis and the hot wire coming out of any socket, you would read 120 volts AC. The importance of this is that you should not ever use this meter probing mains current, mains voltage, and you should not use it to troubleshoot any circuit, whether it's an All-American 5 or a newer piece of electronics that is not isolated from mains. You must use an isolation transformer if you're using this voltmeter. Okay, so really important. A couple of other things just to point out at a macro level in this circuit. The first thing is that over here you have your probes, and on DC, for example, you have an isolation resistor right here, and we'll talk more about the resistive network in a moment. But you have a DC probe here and this resistive network, and then you have 2 halves of vacuum tube 2, V2, which is a 12AU7. And this is a triode amplifying section, and that then runs into 2 other 12AU7 tubes. This is V3, tube 3. And there's a resistive network here, and those feed the meter. So this is the bridge part of this vacuum tube voltmeter, and this is an amplifier circuit. The owner's manual has a very readable theory of operations, and I cannot do justice to what they write, what the engineers write in that. So I encourage you to go and review that section if you're interested about the details of how these different circuits work. All right, a couple of other things just to point out, again at a high level. Going back to that resistive network, we if you trace the DC section of the circuit, you have a 22 megohm resistor, and then depending on what range you want to measure, this switch takes on different positions. And electrically, there's this divider network that goes all the way down through here. Okay, and if you add up this 22 mega ohm resistor in the probe, right, and then this is roughly a 46 mega ohm resistor, so you've got 68 mega ohms of input impedance. And then we have 2 like resistors here that are roughly 22 mega ohms, so that brings us up to what, 112 mega ohms so far. Then we've got a 6.8, so call it a 7 just for rough math, so we're up to 119 mega ohms. Then we've got roughly another 2 mega ohms down to here. So you can see how you accumulate up to 120, 122 mega ohms input impedance. And that's just solely a function of this input resistive network. All right. The last thing I thought was kind of interesting to point out is down here on the power section. By the way, this C10, this 4 microfarad, I think it's a 450 volt resistor, had long since dried up, and that needed replaced. And that's the only component that I've replaced in this so far. But getting back to the power line, so we have this 6.3 volts here between the center tap of this filament transformer and one end, and 6.3 between the center tap and the other. The upshot of this is that delivers 6 volts to what is this? This is V3, and V5 filaments, right? But then we have these resistors, these two resistors here, that feed the filament for V2. So we've got a net equivalent resistance that will drop down the 6.3 volts filament voltage to feed V2. Now, what's V2? Well, V2 is this 12AU7A. So that's a 12 volt filament. But we're not running it at 12. We're not running it at 6. We're dropping that down. So we're running V2 at a filament current, filament voltage that is less than what it requires. And in fact, they tell us here that that should read 4.5 volts. And there's a very good reason why the engineers chose to do this, and that's described in the Theory of Operation section of the Owner's Manual. You should go read that. It's very ingenious. For such a clean, simple circuit, it's really an elegant design for this voltmeter. And then the last thing I wanted to point out is this animal right here. Now, I don't have a lot of experience with ballast tubes, but essentially they're resistors, and they're nonlinear resistors. They change as a function of current that flows through them. So you've got again this 6 volt arm going through a ballast resistor, and then there's another potentiometer right here, and these two form a voltage divider, right, and supplies the filament for V1, and that should result in 5 volts feeding V1. V1 is the diode that is in the AC probe. So that's the vacuum tube in this. Okay, so much for the circuit. Now let's have a drum roll, please. Let's turn this on now. And what I want to do is measure some DC voltages and some resistances, and then see how the AC voltage measurement works. And what I'm trying to do here is not assess whether or not this is calibrated. I guarantee you that it will be out of calibration. But what I'm trying to do is to assess what approximately works and what doesn't. So I'll be looking at things like, does the meter go over when I increase the voltage? Or, when I change resistances. When I have a constant resistance and I look at it on different ranges, does the meter act appropriately? So this is not an attempt at calibration. This is an attempt to see what I will be facing when I go in and clean it up more, and see if there are things that pop up that will cue my attention from a troubleshooting perspective. So let's turn this on. One of the comments on the first video was that people were very excited to see the inside of this. I don't think I'm going to show that in this video. Rather, I want to kind of take it through the paces here and identify what we need to check, and check very closely on the inside, and then the next video will show shots of the inside. Okay. Well, so the pilot light is on. That's a good sign. The meter moved when I applied power. That's a good sign. And now it is lower than 0. So let's just see. So that's a really good sign that the 0 adjust seems to work. And let me zoom in here. You see that there's yellowing around the edges of the meter face. I will take that apart and inspect the inside of the meter, and probably try to wash that off with a little bit of water, and see how that goes. Well, this appears to be pretty stable. It's not fluctuating up and down. Zoom in just a little bit more here, You see that if I go over this way, as I change the pot, I've got good range of motion, and as I go backwards, again, good range of motion. So that's really promising. Okay, well, let me set it on the 3-volt scale. And again, remember, I've got the this is my DC probe. It's ugly, but electrically it should function. And what I'm going to do now is I'm going to take the power supply and I'm going to set it initially for 2 volts. And I'm going to just hook it up to the ground line, and for the other side I will hook the positive to the end of the 22 mega ohm resistor at the end of my coaxial cable. Okay, and so it's on the 3-volt scale, so remember we're going to be looking at how far the meter goes over on this bottom DC scale. And I'm going to now turn the voltage on, and that's a very happy thing. Should read 2 volts, or I've got 2 volts out, I should say, and I'm reading, so this would be 1.5, 2 volts, so I'm reading 1.8 volts. It's not a surprise that it's not reading 2 volts. I'm really happy that it's reading that close to 2 volts. Okay, let me bring it up to 3 volts. And again, I'm reading, what, 2.7 volts. Hooray. Okay, let me move it to the 10 volt range. So again, now this is the upper scale, but I'm multiplying everything by 10. Okay. So this is now reading not 2 volts and not quite 3 volts, so about 2.8 volts. Now let me bring it up to 4. And you see it's now reading, yeah, it's maybe 3.7 volts. Now the power supply is putting out 5 volts, and I'm not reading 5 volts, I'm reading, what, 4.6 volts. Okay, and so on and so forth. So you see that as I go up in voltage on the power supply by a volt each time, I see the meter going again in the right direction. So there it should be at 10 volts. It's measuring 10 volts on the Hewlett-Packard, and the power supply is putting out 11 volts. Let's just do this a little bit more. So now on the 30 volt scale, I'm reading just kind of dead on, what, 1. So 10 volts, and again it's putting out 11 volts. So let's just step that up again, a volt at a time. You see it's reacting linearly. For each volt it's sweeping out essentially the same distance on the power on the meter here. 28 volts on the power supply, and it's what, reading just a little over 25 volts on the scale. And there, I'm at the limit of my power supply, which is 32 volts, and I'm reading, what, 28 volts. 25, 6, 7, 8, 29 volts on the HP. So I'm really happy about this. I'm really happy about this. There's clearly some changes in that resistive network, whether it's a dirty switch, film that's built up on the switch that's added resistance, or the resistors, one or more of the resistors has drifted. Those tend to be wire wound resistors, and so they shouldn't drift, but again, we'll look at this. Let me turn the voltage off, and let's now switch this to the ohms function. So I'm going to switch this now over to ohms. All right, and at the risk of committing heresy here, I've taken an old probe that I found in the junk box that happens to be a Uni-T probe, and soldered it onto the probe housing on the Hewlett-Packard 410B, again just for the proof of concept here. Okay, so let's zoom in on the meter again and look at the ohms adjust pot, and you see the ohms adjust pot moves. It doesn't lurch. It's got good behavior frontwards and backwards. So let's set it on the infinity mark there. And I've now got, let's see, get a couple alligator clips here and clip them onto my precision resistors on the DMM checker. Let's go. So the first one that I've got here, let's set R to ×1, and I should be measuring 100 ohms on the resistor, and you see that the meter is a little less than 100. Let's just see what happens if I move the switch back and forth a little bit, and you see it's pretty consistently not reading 100, which is a little bit of a shame, but these things happen. Now let's go up to 1K, and you see there that we're reading over, well, we're not reading over 500, which is what I would have hoped for. But now let's go up to the R times 10 scale, and what are we reading now? We're reading, well, we're reading down around 50, so this would be, what, times 10, this would be around 500. So we're off by roughly a factor of 2. Now, now let's look at, well, that's interesting. So you see that fluctuation there? Oh, and now when I change the switch, when I flicked it back and forth, now I'm on the times 10 scale, and this is a 1K resistor. I'm reading 100, which would be times 10, so that's 10K. So the switch is dirty. If I move it back to 100 ohms on the times 10 scale, I get 10 times 10 is 100. So that's right. That's right. Let's now move it back to the times 100 scale, and I'm measuring a 10K resistor here. And look at that. It's 100. So 100 times 100 be 10 to the 2, 10 to the 2, that'd be 10 to the 4, which is 10K. So the ohms scale seems to be working. Let's move it up to the times 1000 scale. And you see it's just a hair off of 10. Now I'm not zeroing this. I'm not adjusting it for infinity each time. So I don't expect this to be precise. But it is certainly in line with what I expect. So this is the times 10,000 scale, and you see that kind of jitter back and forth. There's clearly some dirt in this switch. But let's put it up on the 100K resistor now, and okay, so there it is at 10, and clearly there's some, so if I just touch the switch and move it, rock it back and forth a bit, it's got some issues. Okay, but it's rock solid on the times 1000 scale. It's measuring 100, and it's a 100K resistor. Okay, so and there we go. So times 10K, and we've got 10. If I move it up one more, it should go down to 1. Okay, and not too far. So it passes the sniff test on the DC measurement, and it passes the sniff test on the resistance measurement. Now, for our final act, let's look at how it performs on the AC sensing scale. Now, for that, let's just move over here. What we're going to do is we're going to set this function generator to measure, to put out 5 megahertz and 2 volts peak to peak, sine wave. And then what we'll do is we'll rock the the peak-to-peak voltage back and forth and see how the HP tracks, and then we'll pick a constant peak-to-peak voltage and change the frequency. This function generator goes up to, what, 40 megahertz, and this allegedly goes up to over 700 megahertz. So we'll see how that works out. All right. So the first thing to notice is that when I hold this now, it was cold when I turned it on, but this is now softly warm. There's definitely a vacuum tube in there that's on and functioning. And so what I'm going to do is I'm going to hook the ground of the, first of all I'm going to put this on AC. I'm going to move this down to 3 volts. I'm going to zero this out. Okay, again, the AC potentiometer has give. Okay, so I'm going to set that to 0, and I'm going to now put the hot wire onto the tip of the RF probe, and I'm going to hit the output. I'm going to put the output on, and look at that. It shows meter deflection. Again, very, very good, very exciting. So now we're measuring the AC scales, these two down here, okay? And I'm on the 3-volt scale, so I'll be measuring this bottom scale, this one right here, all right? And the signalant says 2 volts peak to peak out. All right, so this is an RMS voltmeter. So let me pull out my trusty, also Hewlett-Packard HP-410B, and just do the math. So I've got 2 volts peak to peak, and I'm going to divide that by 2 square roots of 2. So that should be giving us 0.707, which is obvious if I just thought about it, volts RMS. And down here on this scale, this would be 1 volt, and that would be half a volt. And so, wow, that's 0.6 volts. That is probably accidentally close to being accurate. Okay, let's change the peak-to-peak voltage. So if we go up to 4, then it should roughly double. So that should be twice that, so that should be what 1.4 something. And that is, again, freakishly right on. Again, let's keep going up. So there we're measuring 3 volts RMS, and I've got 10 volts peak to peak. So 10 divided by 2 square roots of 2 should give about 3.5 volts RMS, and I'm measuring, roughly 3 there. So this is really encouraging. Let's move it down a bit, just put it mid-scale there. And now let's change the frequency. So there's 5 megahertz. First of all, I'm going to go down. There's 4, 3, 2, 1. It's not budging. This is great. So back up to 6 megahertz, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 megahertz. Meter hasn't moved. That's great. Now I would expect to see the meter start to move a bit because I have reason to believe that this rolls off when you get closer to 40 megahertz. So let's just keep going. Here I'm at 25, 26, 27, 28, okay, 32, and still pretty solid. Moving down a bit. Okay, there's 40. So I'm there at 40. So, wow, talk about truth in advertising. This meter has fared very well over the years. I did not expect this. I expected that there would be some functions that didn't work, and that there would be all sorts of lunacy when I moved the switches around, and the potentiometers, which kind of notoriously get grungy and things like that. But I'm not seeing that. I'm not seeing any sort of crazy behavior or anything pathological that that piques my interest. So I'll wrap this up. This is becoming much longer than I wanted it to be. You know, wow. What I will do next, and I'll think about how much of this to do on camera versus telling you what I have done after I've done it or as I go along. I will go in and I will check the resistors, particularly the ones in the resistive network, input network, and check those for drift and see if I can identify how well these resistors have aged. These are mostly carbon composition resistors throughout this instrument, and those notoriously drift in age. That's one side of the coin. The other side of the coin is that this was not an amateur instrument. This was a top-of-the-line laboratory-grade instrument, and Hewlett-Packard used the best components when they made this. So on the different internet forums, people routinely say, repeatedly say, don't shotgun change any components in here, especially the resistors, because oftentimes they haven't changed in value very much, if at all. So I'm skeptical of that in this case, because I think that this was around moisture, and this was not stored in peak storage conditions for many years. So we'll see. And clean the switches out. Clearly we've got some dirt here and some grime probably here as well, and so we'll be very careful about changing, cleaning those. Stay tuned for part 3. I hope you found this interesting. If so, please give it a thumbs up below, and as always, thanks for watching.